University of Regensburg. Thanks, Justin.
All right, thanks for having me. Thanks for coming to hear my swan song. This might actually be my last math talk in the foreseeable future. So I'm going to survey some of my some results that I've participated in. Can everyone see the slides now?
Yep, we're good.
One second, I gotta probably see. Yeah, so I'm going to talk about a bunch of different things that I've participated in the recent years with a bunch of collaborators, which I could not list on this front slide. But first, as part of the story, I just want to review some of the non-equivariant story related to nilpotence and periodicity and equivariant stable homotopy theory. So our background, of course, starts off with looking at periodicity. So for our first example of a periodic self-map, we know that for every prime p, there's a self-map of the sphere spectrum. And if you didn't already know so, this map induces an isomorphism in rational homology. So in particular, it can't be, what's going on? Right. Something's happened here. Why won't you click through? Okay. So if I look at the cofiber of this map, S mod P, then Adam showed that this has a self-map, W1, which induces an isomorphism in the first Morava K theory, which can be taken as taking E1 mod P. Here, E1 is p-adically completed complex K theory. So these maps, because they induce an isomorphism in general homology theory, then it follows that all the iterates of them also induce isomorphisms, and therefore they're not zero. So this is a way of detecting whether or not self-maps are nilpotent. Now, this fits into a bigger program, which, again, for some reason, the keyboard is giving me problems. I don't understand what's happening here. I think this must have something to do with the screen share. So sorry about that. There'll be a little flickering between slides. So if we set F0 to be the sphere, F1 to be S mod P, and we can inductively set Fn plus 1 to be Fn mod Wn, where Wn is a periodic self-map, which induces an isomorphism on the nth Morava K theory, which can be constructed by taking this nth Leuven-Tate theory and quotient by its maximal ideal. So it's a big result that such things, these self-maps exist. It's usually a lot of work to construct maps and let alone show they're non-zero. And this is part of what we want to get at. So of course these Leuven-Tate theories are probably familiar to most of the audience here. They're always these higher analogs of these p-adically completed Morava K theories. So by construction of these spectra, their n minus first Morava K theory of Fn is 0, and the nth Morava K theory is non-zero. So these are called type N complexes. Again, even knowing that such things exist is quite a bit of work. So the results of Detmold, Hopkins-Smith tell us about the periodicity in these endomorphism rings of these finite spectra. And then by playing with all the long exact sequences that are given by all these cofiber sequences, we could relate to the stable homotopy groups of spheres. And this is where this program begins. We can find, using these periodicity maps, we can find patterns in the stable homotopy groups of spheres, infinite families. So the first result in, towards this whole periodicity picture is the nilpotence theorem. And I'm going to work with some simpler form of it. So I'm going to have some ring spectrum R, some element in its homotopy. I want to know whether or not that element is nilpotent. Let's assume the element is central. Well, the nilpotence is always equivalent to whether or not if I invert that element, I get a contractible spectrum. If X is central, then by inverting it, I get a ring spectrum again. And we can look at this theorem of Devenant's, Hopkins, and Smith, which says that for such a ring spectrum R, I can see whether or not it's contractible by checking for every prime P, whether or not the FP homology of R is 0, and whether or not all these higher Morava K theories vanish. So obviously the implication from left to right is a lot easier than the other way around. So we can always detect periodic families, non-invertible elements in at least one of these homology theories. One of them, finite things. Okay. There have been some enhancements to this when we assume some more structure. So here's the theorem we had before. If I assume that not just that R is an A infinity ring spectrum, but instead an E infinity ring spectrum, then we get a simpler condition. We can check whether or not the R is contractible if only if it's just ordinary homology with any Richard coefficients of 0. So this is a useful simplification in this case, and can be used to prove a number of nilpotence results that were otherwise unobtainable, because homology tends to be easier to calculate than all of these other theories combined. Or the MU homology is another proxy for those. Okay. So the key part of that argument is just to reduce to the result of Devenant's, Hopkins-Smith. So we take that nilpotence theorem and we say that if I have a commutative algebra spectra, then its nth Morava K theory vanishes for every n and every prime p if and only if the rational homology is 0. So if we know the integral homology is 0, then we already know the rational homology and all the FP homologies are 0. So this is really the key result to getting the rest of these vanishings. Yeah, and of course you can actually just detect whether or not this thing is 0 by looking at pi naught, which again is a nice simplification. So there's a very nice result of Jeremy Hahn, a recent result, came after this. He generalized this result. So he showed that for an E infinity ring spectrum, you could see that if the nth Morava K theory of R vanishes if and only if the nth and all of the higher Morava K theories vanish on R. So when n is 0, we get this key result. I prove with Akil Matthew and Nico Naumann, but this is a nice picture. It seems to show that there's a similar sort of vanishing result for finite spectra, where if you know that the knth homology of X is 0, then you know that the lower Morava K theories of X are 0. So these E infinity ring spectra and finite spectra seem to go in orthogonal directions. In particular, the intersection of those results says that the finite E infinity ring spectra are always of type 0. Okay. So after this nilpotence result is used to prove, amongst other things, this thick subcategory theorem of Hopkins and Smith. So we say that a stable subcategory of p-local finite spectra, so those are the compact objects in the spectra, that's what the omega will denote, is called thick if it's closed and it retracts. So if it's a retract inside of the bigger category, then if it admits a retract in the bigger category, then that retract must be in C. Now we can extend this to that definition say, if I also suppose that for every x in C and every y in P local finite spectra, x tensor y is in, that should be C, that's a typo, sorry. There may be many typos since I compiled these slides today. Then C is called a thick tensor ideal. So you're also closed, C is closed under a tensor with arbitrary spectra in the ambient category. Now, a very useful thing for what's going to come later is to note that if the unit in D generates D as a thick subcategory, then the thick subcategories of D are the same as the thick tensor ideals in D. So the original statement is that the classification involves the classification of thick subcategories, but in fact, it's also the classification of thick tensor ideals. That's a pretty easy exercise. Okay. So, what are some examples of some thick subcategories? Well, inside of P local finite spectra, we have a nested sequence of thick subcategories, these PPNs, going up to PP infinity. This is defined to be those P local finite spectra whose n minus first Morava K theory 0, so that's PPN. It's fairly easy to show that these are, in fact, thick subcategories and tensor ideals. What's not easy to show is that there, in fact, these inclusions are proper, as a bunch of these are not, in fact, equalities. So that's a result of Steve Mitchell from 1985, and it's still an incredibly impressive result every time I go and look at that paper. Hopkins and Smith went up and then showed that these are in fact the only thick subcategories that appear inside of finite P local spectra. And this, I mean, I've used this result before by trying to show, say, a certain map is an equivalence. And saying, oh, it's actually, I can show that it's an equivalence after tensoring with some finite spectrum X. And in fact, the class of such spectra that I can tensor with is a thick subcategory. And the X I chose is in fact type 0. So that means I can eventually build up the sphere inside and see that the original map is an equivalence. It's a very useful trick. And yeah, one of the nicer applications of these kind of results. Okay. So these results all come together in the periodicity theorem. So we say a map, self-map of X, F, it's called a VN map. If this map induces the 0 map on the ith Morava K theory when I is not equal to n, and it induces an ISO for the nth Morava K theory. So in particular, if X has trivial nth Morava K theory, then the 0 map is an example of such a map. So if we let VPN be the full subcategory of spectra, be the spanned by those complexes which admit VN self-maps, then this kind of amazing result is that this category is this fixed subcategory PPN of Kn-1 acyclic finite spectra. In particular, it's a fixed subcategory, which shouldn't be like so obvious. And it's some very, I think, very clever arguments to go and show this. It's not super hard to show it's a fixed subcategory, but it does use the nilpotence results in a crucial way. So we put this together, this lets us realize that there really are these sort of VN self-maps are all over the place. They're somehow generic. Now we're going to shift gears and we're going to look at the equivariant situation. So I'm going to be looking at genuine G-spectra. It's constructed by Lewis May Steinberger, but we're going to give it a somewhat more modern flair. So we'll let G be a finite group. From now on, G is a finite group. Before it was a finite group too, it's just a trivial group. And I look at a G representation V, and I define SV to be the one-point compactification of this real vector space V. So this gives me a pointed G space, and it's a sphere. So special case we care about is the regular representation of G, which we denote by rho G. And now we can define the compact genuine G spectra as a colimit of infinity categories, where I look at the compact pointed G spaces, and I consider the functor which is just smashed with this representation sphere. And I keep iterating that, and this gives me a description of these compact objects inside of here. And this is not just formal nonsense. If you can work with that definition to see what maps are in this category, and you can see that you get this equivariant Spanier-Whitehead category. So it's a useful description. And so effectively what we're trying to do is make smashing with S rho G an invertible functor. So the whole category of genuine G spectra is just the incompletion of this category. So everything else can be constructed as filtered colimits of these finite guys, or compact guys. Okay. So from this description, you can actually immediately see that it's compactly generated, stable, symmetric monoidal, infinity category. Symmetric monoidal requires a little bit of work, so the result of Marco-Roboto shows us that this kind of inversion gives me the right thing, still preserves the symmetric monoidals, or shows that the symmetric monoidal structure in pointed G spaces induces one on this category. It's also useful from this construction that we can write down lots of functors. So how does that go? Well, so there are symmetric monoidal functors, in fact, preserve colimits, or the finite colimits that exist here. So the restriction functor, we restrict to a subgroup H of G for a G space, pointed G space. There's an inflation functor where we pull back a G mod n space, where n is a normal subgroup of G, to a G space. So it just is the same underlying space, but the G action comes from this quotient map to G mod n. And we have fixed point functors. So I can take a G space and I can look at its fixed points. It's not just a space. In fact, there's a residual action by the Weil group of H. So that is the normalizer group of H divided by H. So once you have these functors, you can see that these define maps between the associated colimits, the defining directed systems for G spectra. So these induce symmetric monoidal left adjoints, restriction functor, an inflation functor, and you would think it would be the fixed point functor, but it's what's called a geometric fixed point functor. These are all very nice, well-behaved functors, and by construction, because they come from these functors preserving compact objects, they all preserve compact objects. Just in case you are curious, the right adjoints for these guys are respectively co-induction from G to H, from H to G, which turns out to be the same as the left adjoint to the restriction functor, which is the induction functor. The right adjoint to the inflation map is the n fixed points. These are called the categorical fixed points. In particular, when n is equal to G, you get the G fixed points. And the last one also has a right adjoint, and I leave that one as an exercise for you to write out. it's not going to be your favorite right adjoint. We say that. Okay, so these functors are our friends. They relate all these different categories. They're very well behaved. And part of our goal is to use them to prove theorems. Okay. So what do we have in the equivariant case for a nilpotence theorem? Well, Strickland observed that the Davenant-Hopkins-Smith result pretty much immediately shows that for an algebra in G-SPECTRA, this guy is contractible if and only if for all primes P and all subgroups H, in fact, you could take conjugacy classes of subgroups, the FP homology of the H geometric fixed points vanish, as well as the anthropomorphic K theories of all those geometric fixed points vanish. The key result, which I forgot to mention here, is that any G spectrum is contractible if and only if all of its geometric fixed points are contractible. So it's actually sort of straightforward to go from here to see why this is the case. So the May conjecture has an equivariant analog, and it's just as easy to extend it, the old one to the new one. So in this case, I have a commutative algebra in genuine G spectra. So that's E infinity in what's sometimes called a naive E infinity ring spectrum. So no norm structures assumed here. But this is still a pretty useful category of ring spectra. So we can see that something is contractible if and only if the homology of R with coefficients in A is 0. So A is the Burnside Mackey functor. It's also what you get when you look at pi naught of the genuine G spectrum. So this, again, is actually one of the more computable Houdon homologies theories that you could have out there. And we also somewhat avoid having to write down all these geometric fixed points, and the calculation becomes smaller. There's also the sort of rational version of our statement. So if I just want to know that the Ln localization of this ring spectrum is a point for all n and primes p, or maybe I should say what Ln R means. If you take the Ln local sphere and in the non-equivariant setting, and then you just inflate to get a G spectrum, that guy we could call LNS naught as well. And then LNR is just given by smashing with LNS naught. And then the symmetric monoidal properties are very nice here. So this is, again, we can now check whether or not this is the case, whether or not something is contractible by checking whether or not the homology of R with coefficients in the rational Burnside Mackey functor is 0. This is even easier because now the structure of rational Mackey functors is very simple or semi-simple. Right, so this gives us some idea of how this goes. This never appeared anywhere. It's unlikely that it's going to appear, but it's actually pretty easy to show because you can just show that, again, the hard part is the implication from right to left. And if you were given that R smash HA is contractible, then you can show that if you look at the geometric fixed points, and you get a map from the geometric fixed points of R smash the geometric fixed points of A down to the geometric fixed points of R to HZ. Because there's always somehow pi naught of this thing is always emits a map to Z. Pi naught of the geometric fixed points of A. So then you can just reduce to the previous result. I didn't really expect everyone to follow that, but it's pretty easy. You can work it out. So this last form, we can really see that if we look at the kernel of the Ravitch map from pi star gr to this HA tensor R, pi star G HA tensor R, this is nilpotent. And I use the fancy star, and that's because I can use a fancy star. So even in the G sphere spectrum, if I allow, say, ROG graded elements, there are elements in non-trivial ROG degree which are actually non-nilpotent, but they have non-trivial image under this map. So whatever your flavor is, this result works just as well if you want to move over in this context. And I think Nico has advertised this in the past, but I think we should maybe bring back some of our attention to understand what pick of SG is fairly explicitly for some cases. Quite a lot is written down, and even sort of, it's just a little bit of work to even parse somehow what we know, but it's an interesting area. So a special element that we might be interested in is where I take the reduced regular representation. So I just quotient by the diagonal, the regular representation. That's a trivial representation inside of there. Then the induced map from including 0 into this vector space induces a map between the one-point compactifications, this Euler class, equivariant Euler class. Should we write E rho tilde G. So one reason to care about the nilpotence of this guy is, well, after we invert it, so I can just smash this colimit system with any x, so I can invert it in any G spectrum. And I look at the G fixed points, then I get the geometric fixed points of x. So somehow knowing the nilpotence of these different Euler classes tells us a little bit about where our G spectra are somehow supported in terms of subgroups of x. So it's an application of all this. Let's see, should maybe move along. So if I fix a family of subgroups, so that is, if a subgroup is in my family and some other group is subconjugate to it, then that group has to be in there. Like, so it's closer in taking conjugation and subgroups. So that's what it means to be a family. Then we can define a full subcategory of G spectra called F nil. And we said this is the smallest thick tensor ideal containing G mod H, tensor SG, where H is in the family. So this tensor with a G space is really just tensoring with sigma infinity plus G mod H. Okay. It's a simple definition. It includes in particular those finite G spectra that are built with isotropy in F. But because it's a tensor ideal, it's closed under a lot of other things. There's a lot of other things in this category. So some more notation. We're going to let OGF be a full subcategory of OG, a full subcategory of top G. So that's a full subcategory of the orbit category. So the subcategory of G spaces spanned by the orbits, transitive orbits. And I have to, for OGF, I need to add this extra condition that the G sets have isotropy now. Okay. So we got a bunch of notation here, nothing super hard. So Akil Matthew and Nico Nauman and myself, we proved a recognition theorem. So if I have some G spectrum EG, F a family of subgroups of G, then the following are equivalent. EG is an F nilpotent spectrum. EG is equivalent to a homotopy limit over this orbit category, subcategory of the orbit category, over these EHs. So I unfortunately did not define that. EH is just functions from G mod H plus to EG. That's all it is. That's obviously a functor on this orbit category when H is in F. It's not just that, we have another condition here. There has to be some n such that for every G spectrum, there's a homotopy limit spectral sequence induced by that equivalence, converging now to the EG cohomology of X. That spectral sequence has to collapse at En plus 1 onto the first n rows. And that n is independent of X. In particular, it holds for X being EG. So it's a very strong condition here, and one that yields a lot of computational consequences. Just knowing a spectral sequence has to collapse onto finitely many rows can be used to imply a lot of differentials. And here's the relationship to nilpotence. If I look at the endomorphism ring of EG, then EG being F nilpotent is equivalent to these K geometric fixed points vanishing on it for all K that are not in the family. So all of those Euler classes need to be nilpotent. Okay. So all three parts of this tend to be pretty useful. Once you show that some spectrum you care about is F nilpotent, the fact that that's
sorry, Justin.
That's right.
Justin.
Lets you build up lots of examples from that one.
Justin.
Yeah.
Sean, I think Sean Tilson maybe has a question.
Yeah, I'm curious. So you have these three conditions that are equivalent in applications or in practice. Sort of, what's the most useful direction or most interesting direction? Like, do you use one being equivalent to two to then reduce a lot of computations, or?
Somehow. So many things, all directions seem to be useful in this case. The geometric fixed point property 3, that can be actually checked in many examples. In particular, if EG is a ring spectrum, then the endomorphism ring is an algebra under the EG endomorphisms of EG, so just the ring spectrum EG itself. So you could just check whether or not the geometric fixed points vanish on EG. And if EG is complex orientable, then you could check nilpotence for these Euler classes just in the ordinary grading of EG. So in those cases, you can sometimes use the spectral sequences to check nilpotence. So if you know it's nilpotent for a bigger family, you want to see if you can get down smaller, you can check whether or not these Euler classes are nilpotent via the spectral sequence. Knowing that this, again, it's like showing that things are F nilpotent lets you do things like tensoring with an arbitrary spectrum and taking retracts. And this lets you get from many things that we can pass from Borel equivariant EN cohomology to the LN local sphere, Borel equivariant LN local sphere using that trick. So you can use 1 and 3, actually in some sense all 3 come into play into checking different examples. Once you know these things, the 2 is where you get all these sort of computational consequences. You might actually just want to calculate, the equivariant K theory or something. And you can use this fact that it has a strong convergence property to deduce differentials or prove a number of formal statements. Is that
cool?
Sort of answer your question?
That's fantastic. Yeah, thank you.
Yeah. So some corollaries of this. If you're nilpotent for 2 different families, then you have to be nilpotent for the intersection of those 2 families. That's sort of easy to see from condition 3. So that in particular implies there's a minimal family for every EG. where it's nilpotent. We call this the derived defect base. And it seems to be a bit of a, I don't know, a fingerprint of some sort of useful invariant on G-SPECTRA, what the derived defect bases are. Not only do you get the equivalence to this homotopy limit, but you also have an equivalence from a homotopy co-limit. Since these end up being, EG ends up being both a sheaf and a co-sheaf for sort of these orbit categories. Well, you can make them into co-sheafs for finite G sets, where you define covers to be maps that are induce surjections on all the fixed points for, or H fixed points for H and F. So for each of those two, the whole colim and the whole lim, we have rapidly converging spectral sequences. One using derived functors of the limit, and another one doing derived functors of the colimit. Both have vanishing lines. The lim one tends to be more useful because of multiplicative properties. You can put those things together. So these spectral sequences have edge maps. So from the whole colim spectral sequence, I have the ordinary colimit, and from the whole lim spectral sequence, I have the ordinary limit. And if I look at these two edge maps, I could try to ask how close are they to being isomorphisms. Well, a result of Dress shows that there's a number dividing the group order, such that, depending on the family, such that for every element in positive degree, it's torsion for this natural number. In particular, if you invert the group order, all the higher terms in these spectral sequences are 0. And the rapid convergence tells you can even commute tensor inverting the group order through the whole lim spectral sequence. So you put those together, and it says, in particular, that these induction and restriction maps are rational isomorphisms. These are sort of generalized ARTIN induction theorems. If you don't care about torsion, then you can manage to reconstruct the group cohomology from the cohomology of subgroups. There's also a result like this for homology. There's also a generalization of Quillen's F-ISOMORPHISM theorem. It comes from all this. So if I assume that my spectrum is not just self-nilpotent, but it's also a commutative algebra, I really require very little. But if I take a G space X, then if I look at this edge homomorphism from the cohomology of X to this limit over the H equivariant cohomologies of X for H in the family, then that map is P locally an F-isomorphism, which is roughly an isomorphism up to nilpotence. The kernel is a nilpotent ideal, like bounded order. We know what it is. And everything in the target up to a P power is in the image. Okay. This also can be lifted up to the level of module categories. So again, if I have a commutative algebra that's also F-nilpotent, then I can look at its category of modules. And the restriction functors induce maps to the module categories of the H equivariant subcategories. And this is in fact a symmetric monoidal equivalence. So the entire infinity category can be recovered from for the G equivariant thing from the H equivariant things, H in the family. So this also leads to PIC graded spectral sequences. So because PIC commutes with this whole lim, you'll get an associated spectral sequence for calculating the card groups. Okay. So yeah, maybe some of you have seen this before. I'm very proud of this list of examples. So we have, I'm not going to go through this in any real detail here. On the left, I have a bunch of families of subgroups. And on the right, we have a list of genuine G-spectra. And we identified for all of these G-spectra their derived defect base. What's important, on the right-hand side, everything below that line in the middle of the page, those are underlying spectra. Those are the Borel equivariant cohomology theories associated to the non-equivariant spectra we love. So they just represent Borel equivariant cohomology in this coefficients in the spectrum that is underlined. So if we look at this, we have genuine equivariant complex and real K theory. And those are nilpotent for the cyclic subgroups. So you actually, using the fact that pi naught of these things is the representation ring, you get the actual ARTIN induction theorems, as well as an F nilpotence type statement. If we look at Borel equivariant MU, then we can get, it's nilpotent for a billion P groups, where P is allowed to vary over the primes. And that's gives the ARTIN induction result there as a result of Hopkins, Kuhn, and Ravenel. If we do HFP equivariant cohomology, Borel equivariant cohomology, it's nilpotent for the elementary abelian P groups, so finite FP vector spaces. And we actually recover a classic QUILLEN's result for FP isomorphism theorem, or F-ISOMORPHISM theorem. Then there are a bunch of our chromatic friends. So Lubin-Tate theory gives rise to abelian P groups generated by n or fewer elements. That's the same defect basis for the Ln local sphere. TMF gives me abelian groups generated by 2 elements. This is, we get about commuting 2 tuples in the group. The connective guy has a mixture, connective TMF with the elementary abelians and these abelian 2 groups. And then there are these various Wardism spectra. So you'll notice that all of the chromatic friends are nilpotent for abelian subgroups. And somehow, if you can get smaller, the size of the family seems to be related to the chromatic height. Okay. Let that sink in. Good. So you can actually calculate these whole limb spectral sequences. Sometimes it's a bit more work than you would like it to be, because calculating derived functors over these orbit categories requires a bit of work. So here's an example where we sort of know the answer. So I look at equivariant K theory, complex K theory. I look at the group C2 cross C2. We can use the spectral sequence to calculate the equivariant K theory of a point. So we know the answer, but what does the spectral sequence look like? Well, it turns out to be a bit of a mess. There's a whole lot of higher cohomology terms. They're all 2 torsion. All those little dots are simple 2 torsion. The colors indicate that they show up in 2 different families during the calculation. And we get an induced pattern of differentials. In particular, out of the 0 line, where I look at the limit of the representation rings, there are 3 Z classes. Those are the augmentation ideal. Those correspond to the augmentation ideal of the representation of the cyclic subgroup. And they all support a differential hitting the same element. So appropriate differences survive. It's a kind of fun calculation, and also it's not just for its own sake. You get a bound on what the vanishing line, the height of the vanishing lines have to be. Since this one has a D3 differential, we know that this, we cannot have spectral sequences collapse at E3 in general. I wouldn't be surprised if this is fairly close, up to maybe a multiple of 2, what the nilpotence order is. Also, if you want to calculate the Picard group of the modules over equivariant K-theory, this is a key calculation that you want. And you can say more about it, but you just play a lot of long exact sequence arguments to calculate these E2 terms and import certain differentials. It's fun. And for different things, it can be a bit of a challenge. Kuhn van Woerden, my former PhD student, did a whole bunch of these calculations for F2, Borel equivariant F2 cohomology, and determined nearly perfect bounds for all the exponents there for all groups of order up to 16. It's really beautiful work. So what about this analog of the thick subcategory theorem? Here, the unit doesn't generate the whole category, so the better analog to look at is thick tensor ideals. So for every subgroup H and G, there are a sequence of thick tensor ideals. These guys are determined by just taking the ideals we knew before from P local finite spectrum and looking at those spectra whose H geometric fixed points, P localized, land in that thick subcategory. Okay. Of course, these inclusions come from the inclusions that we knew before. So these are not just thick tensor ideals, they're prime tensor ideals. So they satisfy the expected condition here. If you have two elements who tensor to be in this prime ideal, then at least one of them needs to be in that prime ideal. So Balmer and Sanders, in this Invenciones paper from 2016, showed that, well, this is almost all the prime ideals. You have to add in a sort of generic points, which correspond to the torsion finite spectra. And look at all those things whose geometric fixed points are torsion. And these are precisely the prime thick tensor ideals in genuine G, that should be compact genuine G spectra. It's a nice result. What does this have to say about the classification of actual thick tensor ideals? Well, so given a finite G spectrum X, I can define a function, fx. So this goes from subgroups of G, really should be subgroups of G up to conjugacy. Take a subgroup of G and a prime number, and gives me a number 0, 1, all the way up to and including infinity. We define this function by saying for fx HP is going to be the type of the H geometric fixed points at P locally. So exactly what's the smallest thick subcategory it lands in. Okay, so we're looking at our G spectrum and we're examining how the type vanishes as we vary the subgroup. So if I look at it for a given spectrum X, I look at all the Y in SPG such that Fy is greater than f of x, that is for every H and P, the value is strictly greater. This forms a thick tensor ideal called the supportive X. And now we get to the crux. So Balmer showed that when you knew what all of the prime ideals are, and the inclusions between them, then you can get, you can classify all the tensor ideals, the thick tensor ideals. In this case, they're precisely those that are obtained as the union of these, as unions over these support ideals. So I can take an arbitrary union of such things and I get a thick tensor ideal, and they're all obtained this way. Okay. So to summarize that, to classify the thick tensor ideals in SPG, finite compact G spectra, what we need to find are what functions have this form. So we weren't able to solve this in full generality. This was Tobias Bartel, Marcus Hausmann, Nico Naumann, Thomas Nikolaus, Nat Stapleton. But we were able to do this when G is abelian. We're also able to do it for Dedekind groups, so groups where every subgroup is normal. Well, that's like abelian plus Q8 plus a little bit. So it's not a lot of extra examples that way. So if I have some function, now the question is whether or not there's a function of the form fx that equals this. This happens if and only if, for every chain of subgroups, A1 and A2 instead of A, which is G, I have an inequality here. F of A1P needs to be less than or equal to F of A2P, plus the dimension of this FP vector space, A2 mod A1 tensor FP. Now, I know Nico talked a bit about this, so I'm going to also move through it fairly quickly. So the ingredients of this proof. So first, because all the subgroups are normal, you can reduce to the case that A1 is the trivial subgroup, A2 is the whole group, A. And now we can look at a CP to the K complex for this elementary abelian group of Aron, Dwyer, and Lesch. What does this complex have going for it? Well, non-equivariantly, it's type K. If I look at its fixed points for one of these subgroups, CP to the K minus N, then the height drops by appropriately. So that should have been, yes, K minus N. Okay, once you have such a thing, then you can take a map to A tensor FP, and then take any map, map into CP to the K, and you can inflate. This gives me an A complex. And if I look at its dimension function, it's where the inequality we have is strict. So it's an inequality. So this shows in what this is one of the bounds we need to show. For the other bound, we need another result. So if we look at these Borel equivariant cohomologies, Lubin-Tate theories, and then we look at their geometric fixed points, these have the same Gauss field class as En minus this dimension of this vector space. There's a typo, I'm missing a parenthesis. But so that the chromatic type of En drops by this P rank, which is of A. For abelian subgroups, this is just the same as the number of generators, the number of generators for the P torsion subgroup, which showed up before. In particular, if A, if this P rank of A is greater than N, then in fact the geometric fixed points vanish, and that shows up in this derived induction theory result. So what happens when you do that, if you supposed you had something that broke our inequality, so something whose underlying type is bigger than the amount expected by this, which says, let's suppose it was bigger than N, then this, if I look at the maps from X to this En, well, that guy just calculates the Borel equivariant cohomology of X. And so that just depends on the underlying, it's constructed as a homotopy fixed points of the maps from Fx to En. And since those are contractible, because that type is greater than N, this whole thing is contractible. But if I look at the geometric fixed points of this function spectrum, well, it'll commute right through that function spectrum, because X is finite. And then we get something who has the type, we get a cohomology of phi A of x with coefficients in this phi A of the underlying En. And we're supposed to detect whether or not x is non-trivial there. So we know that that actually can't be zero by our hypothesis of the right-hand side of this inequality. So that's it. So what about the periodicity theorems? That's a really good question.
Hi,
Just take an example. So we take G equals CP.
Justin?
Yep.
Just to let you know, we should wrap it up here in just a couple minutes.
Yeah, I got it. This is second to last slide.
Okay, great.
So if I look at the sphere spectrum, there's a self map. The pi naught of the sphere spectrum is the Burnside ring. So there's an element there which corresponds to the free CP set. So I can look at the cofiber of that, S naught mod CP. Non-equivariantly, this is the Moore space. So S naught mod P, which is type 1. And if I look at the CP fixed points of it, then it actually splits into an S naught by just 1. Essentially, the map we took a cofiber of is 0 on CP fixed points, which is so we get something type 0. So the geometric fixed points emit self-maps of different periodicities. So our results about this, or this classification results show that this is a generic phenomenon. Such examples are in abundance. So here are some questions. Can you lift these non-equivariant self-maps to equivariant maps? I mean, in particular, the type 0 self-map we can lift fairly easily in this example. But the type 1, it's not so clear. It's probably not that difficult, but just can we do it? I mean, how much of this program goes through? Is it possible to sometimes realize the different periodic maps by a single equivariant map? So if I use pick grading, then the geometric fixed candidates can shift the amount of shift we're seeing. So in particular, if I used a reduced regular representation sphere for the shifting for CP, then they have the right degrees, sort of. There's a map that would have the right degrees for a map to realize both periodic maps at the same time. I mean, do we have a notion of a V whatever self map, such that the complexes which emit them are interesting thick tensor ideals? We really don't have any analog of the periodicity theorem. I would also point out, if we could do the thing in red, if we could somehow lift the maps to single maps, it would explain why the patterns in the shift we have do not depend on the height. I could somehow take a cofiber of such a map and get, again, something whose function is exactly the one I had before, plus 1. Yeah. So open questions. I would love to know what the answers are. And thank you, everyone. I will miss all of you. I can't hear you, Dan. You're muted.
I was muted. Questions? I've muted everyone except for Justin to cut down on the background noise, but other questions?
Yeah, Justin, this is Sean. I have another question. You had this thing about the geometric fixed, the Bausfield class of the geometric fixed points of Morava E theory dropping by this dimension of A tensor FP. Is that, does that imply the sort of blue shift results?
In the case of CP, it is exactly the blue shift result. So the blue shift result is really about the Tate cohomology of these, in particular, Morava E-theory. So for that, I want to do some sort of other, for more general groups besides CP. I need to localize not just from proper subgroups, which is what the geometric fixed points does, but from the trivial family. And in our paper, we actually show for abelian subgroups, for abelian groups, what the localizations are for every family. In some sense, we can write down what the drops are if you invert representation spheres. And it turns out that when you localize it some particular family, you can always cover it by affine opens, in a sense, from these localizations. And so there's sort of a descent argument you can see to get the height over any family. And this is explicitly identified. And so in this case, it gives you exactly this blue shift from Nick Kuhn.
Thanks.
Other questions? Well, I've got a question. This is sort of a very, maybe a very naive sort of example, right? So I know that in C2 equivariant homotopy, that the first half map eta is not nilpotent, right? So somehow that should be some sort of counterexample. Some condition must fail there. Can you sort of put your finger on exactly what is happening?
Well, that guy is detected in the homology of the Redon homology with Mackey functor coefficients. Like when you look at it there, when you write it out, I mean, you can really see the periodicity. That guy shows up right there. So basically, you need a slightly more receptive homology theory to be able to catch those sort of guys. Mm-hmm. In particular, you need to get all these representation sphere Euler classes because pretty much they're never nilpotent on the sphere. Mm-hmm. So this is one reason that you naturally are led to thinking about this more inclusive homology theory. It's the simplest one I could think of that detects these nilpotence ones. But really, you just need something whose geometric fixed points augment to HC for every subgroup.
Okay, got it. Okay, other questions?
Great.
Okay, great. I'm going to unmute everyone one last time. Let's thank Justin one last time.